Welcome to Stereochemistry. I am Dr. Baburaj Bhaskar, Associate Professor, Department of Chemistry, College of Engineering and Technology, SRM, Institute of Science and Technology, Katankulattur. In this topic, we will be discussing the basic concepts of stereochemistry. Let me start with introduction to stereochemistry. Stereochemistry is the study of how atoms or groups arranged in three-dimensional space within a molecule. Some molecules, in fact, exist as mirror images. They are called enantiomers, similar to our left and right hands. The three-dimensional shape of molecule can certainly influence its reactivity and biological activity because of the groups or atoms arranged in spatial orientation. It includes both geometrical isomers, such as cis and trans forms, and also optical isomers, enantiomers, and diastereomers. These will be discussed in detail later on, the cis and trans geometrical isomerism, as well as the optical isomerism and their optical activity, etc. And also the special 3D notations. Since the chiral molecules are in three dimension in nature, it's very difficult to depict on board or paper with the two dimension. Therefore, the certain projections are very helpful in order to overcome these issues such as Fisher projection, Newman projection, Saar's projection, and also flying wedge formula to represent these three-dimensional structures. Stereochemistry is a key part of chemistry with applications in biology and medicine, especially for understanding molecular shapes and behaviors. We live in a chiral world. Many molecules exist in forms that are mirror images of each other, called chiral molecules. Chiral molecules are like our hands, mirror images, but not superimposable due to their distinct 3D geometry. In pharmaceuticals, different hands, uh, these are called enantiomers, of a chiral molecule can have different effects. One could be therapeutic, the other possibly harmful. Therefore, controlling which chiral form is produced is critical in drug design and development to ensure safety and efficacy. It is important to know that stereochemistry mainly deals with the property of molecules in three-dimensional space. In early days, molecules were seen in 2D plane when they wanted to understand the reactivity and structure of molecules. The most difficult part of stereochemistry is to visualize the molecules in three-dimensional space because it's a spatial orientation. And it's important to understand when it has started. The particularly optical activity, it is important plane polarized light. Christian Huygens, who lived in between 1629 to 1695, discovered plane polarized light where he has conducted several experiments using the crystals. Later on, Jean-Baptiste Biot, who lived between 1774 to 1862, he has come up with the plane polarized light using the solution state. And later on, the notable person, Foster, who lived between 1822 to 1895, he got the breakthrough when he passed the plane polarized light using the racemic tartaric acid obtained from grape juice fermentation, where he converted the racemic tartaric acid into sodium ammonium salt and separated by hand because of the difference in the crystals. These crystals with the equal opposite rotation that showed clearly that it rotated the plane polarized light. One is in the clockwise direction, the other one is in the anti-clockwise direction. So they show the optical activity. However, another form of tartaric acid, such as mesotartaric acid, that did not display any optical activity. That's something could not be explained at the time. Later on, it was explained, so it was kind of a setback for them, not be able to understand why the mesotartaric acid did not display the optical activity. And then later, both Joseph A. Lebel, that who lived between 1847 and 1930, and Jacobs went off in 1852 to 1930, both were lived in the same era, have proposed that carbon with the four different groups in tetrahedral arrangement are the reason behind the different forms of tartaric acid, why they display the optical activity. However, the tartaric acid, mesotartaric acid could not display any activity. So if you look at the history, initially plane polarized light was discovered, and then molecules rotating the plane polarized light. Later, tartaric acid was found to exist in both optical active and inactive forms. That is the racemic tartaric acid and mesotartaric acid. There was a logic behind it. The molecule carbon with four different groups. At the time, they thought that carbon with the four different groups, uh, it can display the optical activity. However, when they discovered mesotartaric acid, that was found to be some kind of setback. They did not know the exact reason. Later on, it was identified. Let us see, later slides how they overcome all these issues and they could solve. At present, how we effectively come to know that how these molecules show optical activity. Before that, we have to know isomers are different compounds with the same molecular formula. Uh, there are two different categories. One is the constitutional isomers and the other one is the stereoisomers. When it comes to constitutional or structural isomers, have different IUPAC names. The same, uh, that is, different functional groups, different physical properties, and different chemical properties. We will see in detail different classification on the constitutional isomers or the structural isomers. When it comes to stereoisomers, considerably differs because the stereoisomers differ considerably only in the way of atoms are oriented in space compared to constitutional or structural isomers. They have identical IUPAC names except for prefix like cis or trans. They always have same functional groups, and a particular three-dimensional arrangement is called configuration. Uh, Stereoisomers differ in configuration because they are spatially oriented or spatial arrangement. Now one can see that the schematic representation shows how one can classify the isomerism. There are two different categories. One is the constitutional isomerism, the other one is the stereoisomerism. Though there are several classification under constitutional or structural isomerism, but here we have captured only the four different classification. That is a chain isomerism, positional isomerism, and then functional group isomerism, tautomerism. Let's see one by one with the examples where when it comes to chain isomerism, for example, the molecular formula of these three isomers remains same. C5H12, where pentane C5H12 and dimethyl substituted propane is a C5H12, whereas single methyl substituted butane also same. They have the different structure, they have the different physical and chemical properties. And the next one is these are called the chain isomerism. When it comes to positional isomerism, the functional group differs in their position. One butanol, there is a alcohol is attached in the first C1 carbon, whereas 2-butanol, the alcohol group is attached in the 2 position. Therefore, they are called positional isomerism. And third one, functional group isomerism. As we all know that functional group means it could be alcohol, aldehyde, ketone, any other halogens. They're all functional groups. Hence, one can say that here ethanol, it has the OH functional group, whereas ether, it has the oxygen as functional group. But when you talk about the molecular formula, both of them have the same molecular formula. C2H6O. If you calculate the molecular formula on ethanol as well as dimethyl ether. And next one is tautomerism. Tautomerism, where keto-enol tautomerism is a very good example, where acetone it has the keto functional group, whereas enol, the same acetone is converted into enol, where en and alcohol OH group is present in it. These are kind of tautomerism, but molecular formula remains same for both, and whereas structure uh, for these two compounds are different. And now let me move on to the stereoisomer. It's a very interesting one. When you talk about stereoisomerism, the molecular formula would remain same, and also the connectivity of the atoms would remain same. Only the spatial arrangement of group would differ. Therefore, one should not think that cis and trans isomers are kept in the stereoisomerism category, because we will see why it is kept in the stereoisomerism category. Before that, we will see optical isomerism. Optical isomerism, the term says that optical, that is it shows optical activity. When you place it in the polarimeter in a solution, that would either rotate in a either clockwise direction or anti-clockwise direction. So optical isomerism category, there are two different uh, molecules. One is the enantiomers, the other one is the diastereomers. When it comes to enantiomers, where you can say that the simple definition is that they are mirror images. Two enantiomers, they are mirror images, whereas they are not superimposable. They cannot be superimposed. They are called enantiomers. And when it comes to diastereomers, they are neither they are mirror images nor superimposable. When it comes to enantiomer, they have different, same chemical and physical property. Whereas when it comes to diastereomer, they have different physical and different chemical properties. And when it comes to geometrical isomerism, as I mentioned earlier, cis and trans isomer, if you see the carefully, cis and trans, both the side of the carbon atom, same groups are attached. One side is carboxylic acid and hydrogen, the other side hydrogen as well as carboxylic acid. But only difference is they spatially, the spatial arrangement differs. One is cis, the other one is the trans. Therefore, it is kept in the stereoisomerism category. But these two uh, molecules, cis and trans, they don't display any optical activity. Stereochemistry attracted more attention after the thalidomide tragedy. In November 1961, the thalidomide, the two enantiomers R and S, if you look at carefully, the R thalidomide is sedative and the S thalidomide is teratogenic. These two enantiomers, initially they are administered to cure the morning sickness for pregnant women, but it worked very well for the intended purpose. At the same time, uh, it led to a lot of issues for the babies, serious birth defects in more than 10,000 children, about 5,000 of them in West Germany, after the Second World War. It led to several deaths, approximately 2,000 children. That's due to the stereochemistry involved in it. That is the two enantiomers R and S, as I mentioned. One is sedative, other one is a teratogenic. Until then, it was not understood the importance of the stereochemistry of particular enantiomer. They did not analyze properly. After this incident, that was subjected, all the molecules having the stereogenic center or optical activity should be explored in depth for their biological activity. As we all know, the enantiomers, they have the same physical property and the same chemical property, whereas they have the different biological property. That was subjected uh, very thoroughly, and thereafter the development happened rapidly for the stereochemistry in terms of separation, in terms of biological activity, in terms of development of various uh, stereoselective synthesis in terms of when it comes to chemistry, and also the checking the biological activity. Now let us talk about enantiomers. Enantiomers are a pair of molecules that exist in two forms that are mirror images of one another but cannot be superimposed one upon the other. For example, very good example is DL plus or minus lactic acid, whereas you can say the small d and L, they denote the rotation of the polarized plane polarized light, the plus and minus. D is the dextro, L is the levo. Dextro is the clockwise direction, that is a positive sign, and L is the levo rotatory, it's a anti-clockwise direction. So one should not get confused with the small d and L and capital D and L. The capital D and L, that would denote the stereochemistry, whereas small d and L, that would denote the rotation of the plane polarized light, similar to plus and minus sign. So if you look into that, the two enantiomers, they are mirror images. At the same time, they are not superimposable. A pair of enantiomers is distinguished by the direction in which, when dissolved in solution, they rotate plane polarized light, either dextro, that is a D or plus, as I mentioned earlier, or levo, L or minus, rotatory. Hence, the term optical isomers. When enantiomers are present in equal proportions, they are collectively referred to as racemic mixture, and it doesn't rotate polarized light because optical activity of each enantiomer is cancelled by other one. In this slide, one can see uh, the diagrams where the first one shows that it's the levo, anti-clockwise rotation, levo or negative sign enantiomer, anti-clockwise rotation, whereas in the next one, D dextro or positive, that is a clockwise rotation, whereas if the mixture contains both D and L, that's both the enantiomer, they are called racemate, DL as well as plus and minus, hence the net effect would be zero optical activity. This particular slide clearly depicts the importance of single enantiomer. These four enantiomers, they naturally exist as single enantiomers. For example, S limonene and R limonene. When it comes to S limonene, it has the lemon flavor, whereas R limonene, it has the orange flavor. They both are exist as individual in their natural uh, aspect, whereas S carbon and R carbon, when it comes to S carbon, that is present in the cumin, it has the cumin smell, whereas R carbon as the smell of mint. So these are the very good example why the individual enantiomers are very important. If you combine these two, you cannot get the respective individual smell. Therefore, it's very important to have a single enantiomer in order to have the particular property. Having seen the importance of enantiomers, now let's move on to the diastereomers. Diastereomers are stereoisomers. Of course, they are not mirror images, unlike enantiomers. They are not mirror images of each other and also non-superimposable. Diastereomers, they have different physical property. Individual diastereomers, they have the different physical property as well as chemical property. They have different melting points and boiling points and different densities. But when you compare to enantiomers, they have the same physical property as well as chemical property. Therefore, it is very important to understand the difference between enantiomers and diastereomers. They have two or more stereocenters. That is another important criteria for a diastereomers. If you look at the four different structures, these two are called diastereomers. Of course, they have the same molecular formula, but they have the different uh, spatial orientation. And here, if you look into this, these two are enantiomers. When you talk about the properties of enantiomer, they are mirror images. Though you can see that two different that's molecules having two or more carbons, but in this case, two carbons, two stereogenic center, they are yet called enantiomers because they are mirror images, whereas these two are diastereomers because they are not mirror images. So here again you can see these two are diastereomers. Again these two are enantiomers because enantiomers are they are mirror images and enantiomers are diastereomers. Okay, so one has to understand how to differentiate between enantiomers and diastereomers. Why some of the molecules are found to be optically inactive despite having some stereogenic center. There are various categories, but now let's see this particular example. When there is a equal composition 1:1 of enantiomers in the mixture, the resulting solution is optically inactive. The reason is external compensation or cancellation due to opposite optical rotations. That is nothing but racemic mixture. The racemic mixture contains 50 of one enantiomer, 50 of another enantiomer, S as well as R. The rotation, if you look into that, one is having plus 13.5 degree, whereas the other one minus 13.5 degree. When they are present in equal amount in a solution, so one would rotate in a clockwise direction, the other one would rotate anti-clockwise direction. The net result would be the zero optical activity. Hence, you will not see any optical activity. Therefore, they become optically inactive. These are called racemic mixture. Of course, there are other molecules they don't display due to other reasons. For example, earlier we had seen mesotartaric acid. Despite having two stereogenic center within the molecule, half of the molecule would rotate in a clockwise, the other one would rotate in the anti-clockwise. Therefore, they nullify each other in a mesotartaric acid. Hence, that would not display any optical activity. That is another example, another category. And similarly, people came across several uh, other issues. Uh, they had, each time they could come up with overcome the issues and solved it. Let's see one by one. Now, let us see how optical activity is measured using the polarimeter. This is the polarimeter. Entire instrument is called polarimeter, and it requires the light source and then polarizer and also polarimeter tube, where when the light source, when you turn on, it irradiates 360 degree, that is the light radiation. And this unpolarized light, when it passed through the polarizer, that would rotate in particular direction. That will straighten one particular direction. That is called plane polarized light. When you pass this plane polarized light through the polarimeter tube, which normally contain the optically active sample, depends on the sample nature, whether it is a levo or a dextrorotatory sample. The plane polarized light would rotate either clockwise direction or anti-clockwise direction. That can be seen here. That is called observed rotation alpha. That would be recorded through the analyzer. This polarizer passes the light in only one plane. That's what you are seeing here, and make sure that polarimeter tube containing optical active sample. If it is found to be optically active, then it would rotate the plane polarized light either clockwise direction or anti-clockwise direction. This entire setup is called polarimeter, and it can give us the exact detail about the mixture is present. Of course, we will come to know whether it is negative or positive. That means small d or small l. Small d is the clockwise direction, dextro rotation, and other one is the lever rotation, that is a negative sign. Having seen how the instrument works to get the optical rotation using different parameters, now we need to know how to calculate the optical rotation. Optical rotation depends on uh, various parameters such as concentration of the sample. Concentration of the sample is nothing but the material to be analyzed will be dissolved in particular solvent. It could be anything such as chloroform, dichloromethane, or methanol, ethanol, water, anything in which the sample is dissolved. So we must know the concentration of the sample. It is important, and length of the sample cell, where the polarimeter tube, where we have to know that the length of the sample cell, and wavelength of the incident light, the light which we use in order to pass through the polarimeter tube, and solvent which we use to make the sample, and temperature of the instrument. This all very important in order to calculate the specific rotation, that is alpha of the sample at 20 degree if it is given by. So alpha sub lambda equal to alpha divided by LC, where alpha is the optical rotation in degree, and then L is the path length in decimeter, that is the polarimeter tube, and C is the concentration, the gram per milliliter. Once we know all the parameters values, it is easy for us to calculate the specific rotation. From the specific rotation, we can also easily come to know the enantiomeric excess, because once we know the pure specific sample specific rotation, it is easy to calculate the excess, enantiomeric excess for the another enantiomer. It is important to know what is the primary criteria for a molecule to display optical activity. As we have seen earlier, it was thought in the beginning, if the molecule contains that's a carbon with the 4 different groups, that is the primary criteria for a molecule to show optical activity. However, when molecules such as mesotartaric acid, when it was discovered, that was not showing any optical activity. Therefore, the presence of stereocenter is not a sufficient requirement for molecular chirality. This was a real setback for the scientist to overcome and also identify the real reason, what could be the real criteria to say the molecule will show the optical activity. Though the following stereoisomer tartaric acid possesses 2 chiral center, a pure sample of this compound is optically inactive because of internal compensation or presence of plane of symmetry. This molecule has plane of symmetry. If you just look into that, one half of the molecule is equivalent to other half of the molecule. So one half of the molecule would rotate in the clockwise direction, the other one would rotate in the anti-clockwise. Therefore, they nullify. Hence, it becomes optically inactive. Therefore, it is considered to be achiral. Now, let us see one interesting molecule observation. Earlier, we have seen a molecule with the the carbon with the 4 different groups. They show the optical activity. At the same time, a molecule like mesotartaric acid, despite having carbon with the 4 different groups, they did not display any optical activity. But however, initially they thought that the primary criteria would be the molecule should possess carbon with 4 different groups. But when it comes to this sort of molecule, when we come across this sort of molecule, how can a compound be optically active without a carbon with 4 different groups? If you see that the two molecule, something biphenyls with which has substitution in the ortho position, they have the restricted rotation. These two molecules, they display optical activity. That's because of the restricted rotation. They show that they are found to be mirror images. Similarly, there are other example, allenes. Allenes too, they display optical activity. They are not superimposable. At the same time, they are mirror images. So now one has to understand what could be the criteria for a molecule to display optical activity. If you carefully look into that, initially, initial days, it was thought that the molecule, if it has four different groups, the carbon with four different groups, that is the criteria for a molecule to display optical activity. However, when they came across the mesotartaric acid, that kind of logic was not sufficient, and later on when they come across this sort of molecule, something like biphenyls and allenes without any stereogenic center, but still they displayed optical activity. Now the real question is, what is the criteria for a molecule to show optical activity? What are the things we are supposed to consider in order to rule out the molecule is optically inactive? Now we need to conclude what is the primary criteria for a molecule to show optical activity. For example, the thalidomide, R and S thalidomide, both are found to be optically active because the carbon is having four different groups. There is no doubt. And then when we looked into the other example, the mesotartaric acid, despite having carbon with four different groups, therefore it is found to be optically inactive. That's something which we need to really worry about. And the other one molecule example is biphenyls. Without any chiral center, they too display optical activity. So what could be the primary criteria in order to rule out whether the molecule is optically active or not? So we have to consider that will be discussed in the next part in detail. These are the references for the stereochemistry one can refer in order to equip themselves to solve any sort of problem. Thank you.